Hello, welcome to the next Qdrant webinar. Thanks for joining. Today we'll be discussing the ways of how to create an ultimate hybrid search experience. My name is Kacper Rukawski and I'm a senior developer advocate at Qdrant, and today I will be presenting you different features that were introduced by Qdrant 1.10 that helps you to bring the hybrid search experience for your users. Well, before any other ado, let me just start with explaining all the concepts that we will need in order to turn your existing semantic search system into a hybrid one. If you have any comments, please ask them directly on YouTube. I will be just addressing them at the very end of this session. Yeah, let's get to it. Before we start, we definitely need to review some of the concepts introduced by the latest release of Qdrant, because they are really important if you want to build a hybrid search system. So, first of all, there is no single vector search mechanism. There are various ways of how you can incorporate vectors into your information retrieval system. And the main and probably the most popular one nowadays is just using the dense vectors, a single vector created by from a single piece of text. So you have a sentence, maybe a chunk in a rack system, or maybe some sort of document that has a specific meaning, and a single vector representation tries to encode the overall meaning of that sentence. Obviously, internally, it just creates multiple vectors per each token of that sequence, but eventually, pooling mechanism helps to create just a single vector to represent the overall idea behind a particular piece of text. Those are called dense vectors, and there are many models available out there that can create these vectors out of the box. OpenAI, Cohere, and many other companies build their own proprietary systems, but there are also sentence transformers and many other models that you can use for free since they are open source. An alternative to vector search using dense vectors are sparse vectors. And contrary to the dense embeddings, these ones do not have all the dimensions filled with non-zero values, but here we have just a small fraction of all the values being non-zero, and all the rest, and those non-zero values are just set for each token in a sequence. Those tokens might be words, or that really depends on the way you tokenize them. And the alternatives to dense embeddings, this kind of alternative to dense embeddings is thought to solve the problem of exact match way better. There are different models if you want to use them. BM25 or Splate are the most commonly used choices here. But you are not limited to representing the whole document that you want to store in the vector with DB as a single embedding. In some cases, it makes a lot of sense to store multiple vectors per each piece of text you have, or maybe you have images and you want to calculate multiple representations. And there are various ways you can do it in order to bring multiple representations and somehow utilize them, because obviously that's another thing. And the first thing that you could possibly do is to use Matryoshka embeddings. This is still a new topic. There are some models supporting this kind of embeddings. Basically, the idea is simple. We have the original embeddings, which are pretty high dimensional. Let's say we have over 1,000 dimensions. But those models are trained in a way that allows to take just a few of the first dimensions of that whole vector and treat them as a smaller dimensional model, but still keeping some information. So somehow the first dimensions are just more important to keep the semantic of the overall document. Basically, if you want to use this technique, you need to make sure that your model supports it, that it was trained in order to support this idea. And if you want to have a faster experience for your user, you may just utilize just a small fraction of the dimensions. That obviously will come with a cost in terms of search precision, but it will be also way faster because the computation of the distance will be just smaller. So that's one of the ideas. Obviously, another one is to just calculate the same, calculate multiple embeddings for the same input data using multiple models. But up to Qdrant 1.10, you are just expected to write the code that will be just combining the results on your own. And then latest release just changes the way you can interact with multi-vector representations. And it also enables to use so-called late interaction models. Contrary to Matryoshka embeddings, which would be typically stored as just separate named vectors in a collection, late interaction models require to keep them as a matrix. So this is just a set of vectors, and we don't know how many vectors each document will have, because that depends on the number of tokens it contains. But basically, the idea is that we do not calculate the similarity between individual vectors like we do for the dense embeddings, but here we are just calculating them based on this kind of matrix. So we are comparing all the token embeddings of the document and the query, and they'll then calculate the similarity in a different way. So this kind of models are thought to be way more performant in terms of search precision or quality in general. However, they struggle when it comes to speed, because obviously we have more vectors to compare, and that might be also an issue if you really want to care about the latency and user experience. So there are various ways of how to still use these models and mitigate the risk of just waiting forever to get a single response. Yeah, and that actually brings us to the first practical part of this session. We are just going to use 3 different models and index the data in a Qdrant collection. So let me just switch to the notebooks. And here we are. This is the first notebook, because today we'll be just reviewing 2 of them. And the first one is all about indexing data in Qdrant. As you may see, we are using SciFact dataset that comes from EIR collection. This is a pretty standard dataset in terms of benchmarks. Let me just load it. I'm using Hugging Face datasets in order to load it easily. So under the hood, it will just download all the files. And this is how a single document will look like. So we have an ID, which is an integer number. There is a title. There is a text, which is just some scientific document. And let's also check how many documents we have in total. There are over 5,000 documents available in this particular dataset. So since we want to create a hybrid search experience, we need to have at least 2 methods of encoding our text. We could possibly use 2 dense embedding models and just try to combine the results together. That's also one of the ways in which you can create hybrid search. But we want to use hybrid search built from dense embeddings, sparse embeddings, and late interaction model, such as ColBERT. We will be using FastEmbed, which is another open source project of Qdrant. This is basically a library, a Python library that brings you some of the most commonly used embedding models, dense, sparse, and light interaction ones. And you can interact with them using almost the same interface. So basically, here we will be just creating a single embedding. I'm just accessing the first document and actually accessing the text property of it. I want to create a single embedding just to see how it looks like. Okay, so we have one embedding of this dimensionality. But this is pretty well-known fact because all mini LM L6 V2 is quite commonly used for demo purposes, and it's also pretty fast, even though I'm not running that on GPU. But thanks to ONNX support of fast embed, it is still pretty efficient. And another model we are going to use is BM25. Qdrant provides you with BM25 implementation that actually converts them into sparse vectors. This is available on Hugging Face Hub. So this is just a model you can easily download using Hugging Face transformers. But Fast Embed is also integrated with it, and it's as easy as just passing the name of the model. And then the embedding is calculated for the same document using the same method, passage embed, but we just provide a different implementation of the model. And the last but not least is late interaction text embedding, which is there are like different possibilities here, but I decided to use ColBERT in version 2. And the process is exactly the same. I'm just loading the implementation from Fast Embed. Internally, it just fetches all the required files in order to bring this model to life. And then I can see the dimensionality of a single embedding. This is also pretty interesting to check how many tokens this particular text contains. Because right now I'm just displaying the dimensionality of a single embedding. But please remember that we have multiple tokens, and per each token we'll have a separate embedding. In our case, we have 431 tokens in the dataset, which is not in the dataset, but for this particular example from the dataset, which is quite high, because in a typical setup using just dense embeddings, we only have a single vector. So obviously, if we have a query that will also have several tokens, queries are just usually just shorter, then we would need to make a lot of more comparisons. So that's why the late interaction models will be also typically slower. And the next step is just to put the data into a Qdrant collection. Obviously, we just created a single example for every single model we have. So we still need to vectorize the data. But before we do that, I just need to run a Qdrant instance. So right now, my Qdrant should be already running. And when I check the Docker PS output, I can clearly see that there is a Qdrant instance running. Please remember that all of this might be applied only if you use Qdrant 1.10. Because it really brings a lot of new features that cannot be used in the past version. However, if you use, for example, 1.9, then you can also easily upgrade an existing instance without the need to recompute your data, because we are backward compatible. Please remember to just update a single version at a time. And the next step is actually to create our collection. Here I specifically provided a pretty long timeout, but I will just clarify that in a second. First of all, let's have a look at the collection configuration, because this is quite important. First of all, the name of the collection is SciFact, which is actually the name of the dataset itself, so it's pretty obvious. But then the configuration of the vectors is split into two parts. First of all, we configure all the dense embeddings. ColBERT model also produces dense embeddings. It just produces multiple embeddings per single point. So we have to configure that differently. And we will have two named vectors, I mean the dense vectors. So I like to keep the name of the model as the name of my vector, but this is just my preference. However, whenever I come back to the example I prepared in the past, I can easily say what was the model you used to create it. So I would consider it a good practice. Practically, that really depends on the data. So I have to provide the size of an individual vector here. Also, the distance and cosine distance is the default one. And for the second model, ColBERT, I also specify the length, but this time I need to take care about the length of this individual vector of each token. And then also multi-vector configuration with the comparator. Right now, there is only single option, but that has to be provided because obviously that may change in the future. So just to keep the compatibility of code, it's best to just keep provided explicitly. And sparse vectors configuration. Here we are just going to have BM25. And one interesting addition to Qdrant 1.10 is that you can specify a modifier. And in that case, there is also just a single value that you can set here right now, but maybe there will be some additional ones in the future. But basically, this modifier will calculate the inverse document frequency for the documents you have. So this is pretty interesting feature because that will be automatically reflected whenever you will be searching using your sparse vectors. So that makes a lot of sense. So you don't have to calculate this values on your own and keep them separated from the data in your vector DB. So this is also a pretty new feature and pretty useful if you use sparse vectors. Let me just create the collection. And it was already created, but right now we need to create all the embeddings and store them in Qdrant. So obviously that should be done in batches. Like this late interaction model will produce hundreds of embeddings per each input sample. That means that you will be just sending lots of data per each request. And if you just use the default values, you may encounter some issues with the maximum size of each request. Here I'm just using HTTP protocol. Possibly this batch size could be increased if you are using gRPC, but still there is some sort of limit that you shouldn't be exceeding. And also it makes a lot of sense to just create them in batch so you can track the progress. So I'm just setting it to 4. And what happens next is that I'm just iterating over the data set with this specific batch size, and I'm creating the embeddings using all the 3 models for the batch that I get from the iterator. Then I'm using the Qdrant client, the Python SDK, to upload the points that also have to be converted into a specific structure. The point structure, there has to be an ID, which might be either integer or UUID like string. In my case, since the documents already have a specific identifier, it just makes a lot of sense to keep it as an ID, and they are just integers. So that makes a lot of sense. Still, the datasets library provides them as strings, so so I have to convert them, not to have the validation issues. And then I just send my vectors as a dictionary. So this is a mapping between the names of the vectors and the corresponding embeddings. So dense embeddings might be just provided as JSON list of floats. But in case of sparse embeddings, we are not providing these zeros all the time. That doesn't make much sense. In this case, we need to convert them to objects. And those objects are just keeping the indices and corresponding values separately. So this is specific to fast embed. And when it comes to light interaction models, I'm just producing a list of embeddings, but still this will be just a list of floats. So I can easily send them that way. Obviously, we want to keep the payload. We want to have the original document that we used to create all the embeddings. So instead of just running the semantic search, we can already access the content of a particular document. This is primarily useful if you implement Retrieval Augmented Generation, because you don't want to bring the IDs of the points which are the closest, but you also want to have the text so you can put it into the context of the prompt you set. So we have an ID, we have the title and the text. Also, the batch size might be set on the upload points level. We are not passing more than the requested batch size, but just to make it explicit, I decided to put it here. So let me just run it. And unfortunately, each iteration will take some time. Right now, I was just able to get over 4 iterations. So that obviously will take more time than we expect this webinar to last. So let me just stop that. I just interrupted that process because I have a snapshot. And this snapshot is also available on our Google Cloud bucket. So you can easily recover the snapshot to an existing Qdrant instance and use the data as it was provided. This snapshot is pretty big in terms of the number of points inside. But basically, it's around like 500 megabytes. But if you just want to experiment, it doesn't make much sense to create all the embeddings again. Recovering the snapshot is the easiest way to migrate data between different environments. So that's what we are going to do. And eventually, we can also ask for the collection information. That will be helpful to determine how many points we have inside, but also what is the configuration of a collection in general, and if it reflects what we expected it to. So we have over 5,000 points. So this is actually the number of points in the data set itself that we predicted to have. So that's fine. And this is the number of points indexed. And also all the other configuration you can possibly set on a Qdrant collection. That means we have all the data in place and we can start discussing hybrid search and how to build it. Okay, the data is here, but building a hybrid search is not an easy task. It's actually a challenge because it's not there is not a single way of how to do it. So let me just introduce you some of the basic concepts, and then we'll switch back to the notebook, another one in which we'll be building just a couple of hybrid search mechanisms. So basically, one of the easiest hybrid search solutions is to use a couple of different search mechanisms, such as dense and sparse vectors, and then use the scores produced by these models, obviously after applying the normalization, because they might be just not compatible. If you have dense vectors and you use cosine distance, then you would typically get a range of 0 to 1, because they are just really negative. If you have sparse results produced by BM25, that might be just way higher. So some normalization has to be applied, and then fusion mechanism will just use these scores to calculate which documents are the most relevant. That makes some sense in some scenarios. Definitely, that's not a silver bullet. And reciprocal ranked fusion is one of the methods that is commonly used to achieve that. And this is also another feature brought by Qdrant 1.10. You can build RRF with multiple prefetching mechanisms such as sparse and dense vectors just by calling the new query API. And another family of hybrid search mechanism is reranking. Reranking is a bit more complex because it doesn't rely on the individual scores returned by multiple models you may have, but instead there is another model, usually some sort of neural network, but it might be also some rule-based system that uses the information from the documents, not the scores themselves. Actually, nothing stops you from implementing a model that will be using scores and the documents. But the main difference here is that there is usually a neural model that we cannot run on all the documents we have, because this is just inefficient. It cannot handle millions of documents at the same time, but it becomes pretty useful if you have just hundreds of them. So then if you have some candidates returned by multiple models, you can just put them all into the reranker, and then it will produce another order of the documents, hopefully better than any of the original ones. So this is way heavier process than the fusion mechanism. And thanks to the new query API introduced in Qdrant 1.10, you can create even a complex search pipeline using multiple models. So it will be just providing you both fusion and re-ranking mechanism using different approaches to search. You can combine sparse, dense vectors. You can possibly use quantized dense embeddings if you want, or maybe utilize binary quantization in the first step and then improve the quality by applying a different mechanism. In this example, the first operation done on small byte vector will produce a set of 1,000 results. So 1,000 closest documents to given query. And then full dense vectors won't be used on the whole collection, but instead it will be just launched on all the candidates returned by this small byte vector search. So we'll be just reviewing this 1,000 vectors, this 1,000 objects, and then we will be just limiting them to 100 best matches. So in the first step, we are just taking a lot of documents and then limiting the scope to 100. And then the final step will be just done with multi-vector. Because here, we'll be just expecting to have 10 results, and they will be produced based on the 100 provided by full dense search. So this is a multi-step search operation, and it might be even more complex because you can nest the prefetch operation multiple times. You can provide various operations. You can also implement a mechanism that will start with recommendations, because right now this new query API allows you to use all the functionalities of Qdrant that previously were supported by calling multiple endpoints. Here, you can start with recommendations and then adjust them by using vector search. And only the first operation here will use HNSW search or any kind of data structure, because then we just narrow down the scope of search. And it's any of the methods that is supported will be probably efficient enough to be launched on 1,000 or 100 examples. So that makes a lot of sense, and that actually brings a lot of possibilities to build hybrid search. And right now, we are just going to do a couple of tests to see what works and what's not. Another notebook this time. We are obviously connecting to Qdrant the same way, but our collection is already here, so we don't have to create any new embeddings for the documents, only for the queries. We also have to load all the models we decided to use in our test. So I'm just loading them at once in a single cell. We have this all-mini LM-L6v2, BM25, and ColBERT in the second version. So this is just an example of a query you could possibly send to the system. What is the impact of COVID-19 on the environment? And right now, instead of calling query points, instead of calling search method, we will be calling query points, because this is the new endpoint, this new query API introduced by Qdrant. So similarly to all the other endpoints, we have to provide the name of the collection, a query, and also specify which embedding to use, because we have 3 separate named vectors. Obviously, the name of the vector depends on the configuration. We also specify the number of points we want to have to be returned. And right now, I do not care that much about the payloads. It's not important. I just wanted to show that the output of this method will be just similar to the one you would expect from the search endpoint in the past. So if you are familiar with the previous version of the API, the migration is not a big deal. Okay, we have some scores, we have the IDs of the points, but we do not know what exactly was the response. But here in this notebook, we do not care that much about every individual response of Qdrant, but instead we want to measure the quality of different systems. That's why we need to do some benchmarking. The good thing about the SciFact benchmark is that it comes with so-called QRELs. There is basically a set of queries with well-curated list of the relevant documents for each query. So there is more than 1,000 queries. We also have QRLs, that stands for query relevance judgments. And this is actually a mapping query of the query and the documents which are relevant to each, with some relevancy score. This is how each judgment looks like. We have a query ID. Corpus ID is an identifier of the document we indexed, and score is just an information of how much this document is relevant for a given query. In this case, this is just binary information, so a document is either relevant or not. And everything starts with producing a ground truth data set. This actually will produce the same output like before. And here we will be using ranks library. If you don't know it, I really encourage you to have a look. Ranks implements multiple information retrieval metrics, so you can just use the existing implementation and do not create your own method to calculate precision at K or any other metric you could possibly imagine. And this is really, really simple to use. There are just two main objects you need to understand. There is QRLs, again, query relevance judgments, that might be initialized with a dictionary. And this dictionary should contain this mapping. So every query will get a list of documents, actually another dictionary, and each document will have the score assigned. So we just need to iterate over all the QRLs in the data set we have and build that structure. So this is a simple exercise. And after iterating over it, when I display how this QRLs looks like, you will be able to see that the structure is pretty straightforward. We have a query ID, then the document ID, and the relevance judgment. And that is actually repeated multiple times, because for every single query, we may have multiple results. And one thing to make it just a bit faster, let me just pre-compute all the embeddings, because we'll be just creating multiple hybrid search pipelines. So I don't want to create them all the time whenever I just change some of the parameters. And still, we have to pass these embeddings to the query API. So let's just have them pre-computed beforehand and then use them easily, so everything will be just a bit faster. So it doesn't take that much this time. We are just calculating them, and that should not take more than a minute. And we will have all the 1,000 queries encoded easily, even without the GPU. And after that, we'll be just testing different options to build search experience. And everything starts with dense embeddings, because that would be usually our baseline. If you are a Qdrant user, you probably already have an existing system using the dense embeddings. Maybe you have already incorporated sparse embeddings into your search engine, because they were released before 1.10. But you are probably just combining the results on your own. You are just supposed to write your own system that will be taking this intermediate responses of dense and sparse, and then you will be just typically combining them in some smart way. Right now, we don't have to do it, but it's actually a good practice to calculate what is the precision, what is the accuracy of our search using this original method we had. So we will be using run objects from ranks library, which is actually another dictionary. This time we are just querying using all the queries from the data set. We are taking the list of results, and we are creating a similar structures, because for every single query, we are just taking the point and the score returned for this particular point by our search operation. So this is pretty straightforward, and please just get used to it, because we'll be just reproducing multiple hybrid search operations, but it won't be that different. We'll be just extending the call to the query points. So again, we are taking the query ID, we are taking the pre-computed dense vector, and then query our collection using this vector to then get a list of points returned by the system. let me just run the cell. It should produce this ranks object, and we can give a name to every single run object, so it's just way easier to compare them later. It has already finished. Dense embeddings are pretty fast. That's something that is huge benefit of using them, contrary to some different systems. And evaluation with ranks is really simple, because you can provide QRLs, the run that you want to evaluate against these QRLs, and just a list of metrics as strings. So I just wanted to calculate precision at 10, MRR at 10, and make comparable, just make sure that it calculates the metrics properly if, for example, for a particular query, you do not have any response. So just to make sure that everything works smoothly. So this is our precision. This is the MRR, and still we don't know if it's good or not. Right now, this is just a number, and it doesn't tell much about the quality of search, because we need to compare it to something. So in the next cell, we are going to do basically the same thing, but this time we are going to use sparse vectors alone. So we are building this dictionary again, but this time we are querying using sparse vector. So if you do use sparse vectors, they have to be encapsulated with this sparse vector model and converted into a proper structure. Again, you are not sending a list of zeros that could possibly have few thousands zero values, because that will be a network overhead. So the structure is a bit different. This time, we specify the vector name to BN25, because that's the one containing BN25 representations. And nothing else is changed here except for the names. We are just creating another run and evaluating it using the same metrics. There's actually a question that I think we should answer right now. What is MRR at 10? Mean reciprocal rank is a quite commonly used metric in information retrieval that actually helps you to judge how like often relevant results in the top place. So actually, this is pretty useful metric, because obviously there is a bias, and if you just present a list of results to your users, they will be probably clicking on one of the first options. So that actually takes into consideration only the fact that a relevant product or relevant document was just high in the list. Unfortunately, we cannot go through all the metrics in that session, but the higher the value, the better it is. So that's the intuition. And if we just compare the values of BN25 versus this dense embeddings, we can clearly see that precision is higher for the dense embeddings, and MRR is also higher for the dense embeddings. So probably it doesn't make much sense to just replace an existing dense embedding system with sparse embeddings, because we'll be losing some quality. And we can do the same for the late interaction model. This time is just going to take a bit longer, because we are just querying using multiple vectors at a time. So the comparison is just longer than usually. But if you just see the code here, we are just taking another vector, but all the rest is kept the same. We are just changing the name of this particular run. And this will be definitely the slowest option. And late interaction models are rarely used alone. Obviously, if you have a system that will be accessed by just a few users at a time, maybe you really need to have the highest quality possible. Then you can consider running the late interaction model alone. Probably it's just going to take a little more time. So you cannot expect to have like immediate response from the system. But in some cases, that's acceptable. Maybe not if you create another web application, because in this case, you'll be just losing a lot of time, and people won't just waste their time to wait for the response. They will probably just go somewhere else to find something of their interest. Okay, and that might be running for a bit longer, so let's just give it some time. And let's just discuss the next cell we are going to run here, because it starts using some hybrid search mechanism already. So the first one will be using dense and sparse vectors together, just to see if combining the results using this reciprocal rank fusion makes sense. Our query points call will take another argument, prefetch, and prefetch actually tells how the system should take the vectors and then combine them together in some way. In our case, we are setting the query to fusion query, and we specify the fusion model to RRF, which is the only option available right now. So that's the only difference. All the rest is kept the same. This is still running, so I will just launch that, and it will just wait in a queue, so we can have the results immediately once the previous cell is finished. But basically, that's the whole hybrid search pipeline. It's a single call to our query API, providing multiple vectors at the same time, so they can be just launched in parallel, because both dense vectors and sparse vectors will be launched in parallel. The intermediate results returned by both methods will be just combined together, and then the fusion of the scores will be done. So this is pretty straightforward way. And if you used RRF already with Qdrant, then probably you could consider migration, because that will obviously improve the experience. There is no need to have another tool doing the same job if you can use just Qdrant API alone. Okay, that takes a little bit more time than I expected, but obviously that also shows that late interaction model cannot be used alone, and it's usually a bad practice if you do that, or unless you really need to have the highest precision possible, because I expect that the output of it will clearly show that both the precision and MRR scores are just the highest amongst all the attempts we did today. Okay, we can wait for the response and discuss the next approach to search, which will be using all the methods in parallel. So this time we are just going to call the prefetch method on all the vectors we have, so both dense and sparse like we did for the last time, but also ColBERT. So again, this will be possibly quite slow, because this will be running on the whole collection. It will just produce a set of results, and eventually we are going to combine them using RRF, so the same fusion scheme like before. So I expect it to be quite long, taking quite long, and definitely not the best you can achieve. But since we finally have the result, let me just run this query in the background and discuss the results we achieved by the previous ones. So let's come back to the late interaction model. That was definitely too slow. Like nobody would probably wait such a long time to get a response from an e-commerce search or any kind of rack, even though LLMs are terribly slow. Sometimes, like if this retrieval component is not efficient enough, that will just multiply by a couple of times. So the precision is 0.09, which is definitely higher than sparse and dense. MRR is also higher than for all the other methods we had. So definitely we have a winner in terms of a single search operation. But if we combine the results coming from just dense and sparse vectors with this rank fusion, we can easily get close to the result achieved by late interaction models. But the search latency is just so way better that in the most typical use cases, you will probably just sacrifice the precision because of the speed of that solution. As you may see, if we just combine all the methods, it still processes all the data. So it is slow, unfortunately. So that's not the typical use case for the late interaction models. Typically, we use them differently. So we prefetch some candidates using different methods to search. Like we take some candidates using dense vectors and sparse vectors, and then perform re-ranking using late interaction models. In this case, we are prefetching 20 candidates from dense search and 20 from sparse search. So even though if there is no overlap between both methods, we would end up with maximum 40 documents. So it's not that high number, and that might be easily prefetched, easily calculated efficiently with late interaction models. So nothing changes comparing to the first attempt to RRF, except for the query. We no longer set it to Fusion, but this time we are providing this late query vector produced by ColBERT and specify the vector to use. So in this case, the process will go as following. We're just going to prefetch some documents using both methods, and all the results combined together will be an input to the late interaction model. So it won't be calculating all the distances to all the documents in the database, but instead we'll be just working on this limited data set. And that should be just efficient enough to be run even in a production setup. I will be just running this cell in the background so we do not lose more time, because obviously this is taking forever. This is so long process that nobody's gonna wait for that long. And re-ranking step using late interaction models is probably the most common choice. So we have some efficient methods doing the initial pre-filtering of the data, prefetching of the data, and then this heavy model doing its best job to just re-rank them so they can reflect the user intents best. Obviously, ColBERT or late interaction models are not the only ways to do the re-ranking. Ultimately, any of the search mechanism may also work as a re-ranking step, because if you prefetch some documents using sparse search and then re-rank them using dense, that also makes a lot of sense, because maybe the scope of search is just limited to the best matches that also covers the exact match. That might be your intention, but then vector search brings this semantic value to re-rank the document. So that makes a lot of sense. And actually, the possibilities here are just endless. You can create multiple steps. You can nest this prefetch operation multiple times and just build a really complex vector search operation. But that really depends on the data you have. In a very specific domain, you can just modify the steps of the hybrid search you implement and experiment with various configurations as many times as you want. But obviously, you need to take care about the quality and measure it somehow. So ground truth data set is crucial. Okay, we have the results of all the methods in parallel. So MRR is getting closer to 0.7. So it's the highest possible value we're able to achieve so far. So if you do not care about the latency that much, that might be your choice, because we covered all the possible steps. And here are the results, the best out of all of the attempts we had. And in the meantime, when I was speaking, the other cell has already finished. Even though we used this late interaction model, it was still fast enough, and the results are quite close to the previous ones. So this additional re-ranking step with late interaction model might be still efficient, but also accurate enough. And another thing is this multi-step retrieval process that I tried to describe a minute ago. So it all starts with the dense vectors. We try to find the 100 best matches using the dense search. So hopefully this is going to cover all of the most relevant documents. And then we re-rank them using BM25. So BM25 acts as a re-ranking mechanism this time, and it only works on 100 documents returned by the dense search. And eventually, the light interaction model, ColBERT, will narrow down the scope of search from 50 to 10. And that will be the response of the system. Let me just run it. I also expect it to be really fast. because obviously we are not using late interaction alone, just on a subset of data, and it is just iterating over 1,000 queries. So obviously it's not like immediate response, but still pretty fast. So the results were not that high like before, but as you may see, this is just another approach. And I didn't really experiment with the number of matches each method should respond with, and many other factors that may also impact the quality of your search. Because obviously you can control the HNSW parameters if you want to, or maybe you can also play with quantization. And this multi-step processing is pretty useful if you have Matryoshka embeddings, because you can start your search operation with the lowest dimensionality that you have, and then just extend the dimensionality in every consecutive step. You may be just narrowing down the scope of search. So let's say you start with 1,000 closest matches with the shortest vectors you have, and then you just reduce it to 100, 10, and maybe just 5 best matches. So possibilities are endless. And one thing that I really love about ranks is also that I can compare different runs. And in this case, since I added the name of each run, I can easily see that a particular method was the best in terms of a specific metric that I mostly care about. Obviously, full RRF using dense, sparse, and late interaction embeddings was the best in terms of all the metrics here. But maybe you don't really need to have the best system possible, but you need a performant one. And maybe you can take the second best one from the list and still use it without worrying too much about the quality of search. Obviously, none of the methods alone worked that well. Yeah, and that actually brings us to conclusions. We tested different hybrid search architectures, but there is no one-fits-all approach. You need to experiment with various setups if you really care about quality, but with the new query API, that might be doable easily. Obviously, if you want to compare different setups, you need to have a data set, a ground truth data set that should be well curated, probably created manually. I know that many people just create these data sets nowadays using LLMs, but probably if you have your own data that has its own specifics, that makes a lot of sense to just sacrifice some of time to create a set of most relevant documents for the queries that matters most in your case. And if you want to implement hybrid search with Qdrant, this new query API makes it really easy. You just need to provide multiple vector representations, and that's basically it. You can easily test multiple options without the need to build your own service that will be doing it. And that's actually it regarding what I prepared for today. If you have any questions, please feel free to reach me out on LinkedIn, Twitter, or GitHub. If you are really able to send a message on GitHub, I'm not sure of that. And this QR code leads you to my LinkedIn account, so please feel free to drop me a message. Right now, I would love to go through your questions because there were a couple of them, and hopefully we can spend another 5 minutes. There was a question about the notebooks. Definitely, okay, I see that Maddie has already answered that. Yeah, the notebooks will be available, and the webinar will be obviously registered and uploaded. Yeah, there is a question about fast embed if it supports newer models like Stella 1.5b v5. I'm not sure of that. The list of all the models we support is available on the Fast Embed website. If you have any ideas of what are the models you would like to see there, then please feel free to open a GitHub issue in the repository of a Fast Embed. That might be the easiest way to get your model available there. Probably if it's available on Hugging Face Hub, I'm not sure of that. That might be easily done. Another question is, what is the point of the late interaction model? What does it do? So basically, the main idea behind late interaction model is to not create this similarity between two different objects based on a single vector embedding. Because obviously, if you have a model producing text embeddings, it produces a single representation for all the tokens, but each chunk of your document may cover multiple topics. So obviously, this single vector embedding won't be able to capture all of the details of this particular text. So it makes a lot of sense to create a single embedding per token and then calculate the similarity using this matrix. So each token of the document will be calculated versus each token of a query. Obviously, that increases the memory requirements, but it also shows huge improvement, like what we did. It's just way more accurate in terms of search precision and all the metrics we calculated. It's just not applicable in many production use cases if you care about the latency. So multiple vector representations usually beat methods based solely on a single vector. We have a question about our SDK, if Qdrant 1.10 is compatible with 1.6 or 1.7. Well, I would expect that it should be backward compatible, but we usually just make sure that it's compatible with the previous version. So 1.10 should be compatible with 1.9. And obviously, the version of the library you have should be kept in sync with the version of the Qdrant server you use. So you shouldn't be using Qdrant 1.10 with Qdrant server 1.6. That's why we want to keep this semantic naming, and we keep the versioning of the client packages in sync with the server. This is still a pretty new field, so many interesting research is being done on vector embeddings and vector search. So we don't want to. We just want to be able to bring the best experience possible, the best methods possible, and sometimes that has to be done with some changes in the client itself. Can this query points API be used in combination with prefix search? I'm not sure what prefix search means. Clarification, because that is a scroll operation as far as I understand. Not really, scroll operation is actually useful if you want to export all the points from your collection, or if you just want to iterate all the points in your collection, or find points matching particular filtering criteria without passing this vector embedding to the query. Sometimes you don't want to perform similarity search. So the scroll API is rather designed for that. I'm not sure what you meant by prefix search. I could try to find the answer, but it would be best if you could just send me a message. Does the Qdrant with Llama Index provide inbuilt hybrid search? Definitely, there was a hybrid search in Llama Index in the past, but that was done on client side. So you could provide hybrid. You could implement hybrid search by providing dense and sparse embeddings, and then the results will be combined, but on the client side. I'm not sure about the progress of implementing increasing the coverage of the most recent features of Qdrant in Llama Index, but probably it's either in progress or already done, because we want to make sure that all our users, and we have lots of users of Llama Index and many other frameworks, so we want to make sure that they are also able to benefit from the most recent releases. Okay, what are my opinions on cross-encoders and late interaction models? Obviously, cross-encoders are interesting, but cross-encoders are not that well integrated with vector databases because they take document and query at the same time. So definitely they are not scalable that much. They're usually also used as a reranking step. That makes a lot of sense, but unfortunately, late interaction models win here because you can pre-compute the embeddings of the tokens in the document. So this is just way faster. You don't have to recompute them over and over again. Cross-encoders just need to do it for every single document and query, and since queries are unknown, that effectively has to compute the embeddings for all the pairs. So it's not that applicable in practice. And the last question, is it possible to get more of the complex functions integrated with LangChain? Sure, please feel free to reach us out on our Discord community or just create an issue on GitHub. We have a separate package for our LangChain integration. So if you have any ideas of what we should implement, please just let us know. But you are the users of Qdrant, so you know best what we should bring to life to make it just a bit easier. And I can't see any other questions, so thank you very much. That was a pleasure. And if you still have some doubts regarding our latest release, or if you just want to discuss what are the possibilities in your specific setup, please feel free to do it. Well, actually, I just realized there are some more questions. Unfortunately, I cannot answer them right now. We are just running out of time, but feel free to just drop me a message anytime, or alternatively, I can just go over the comments once this recording is published and then answer them in the comments directly. Thank you very much. Thanks for joining, and hopefully see you next month on the next Qdrant webinar.